Okay, for topic three, we're going to start looking at the graphs of polar equations. So we're going to look at some where perhaps the rectangular form is going to be pretty easy for us to work with. And then we're going to look at some later where the rectangular form is absolute bonkers. And so we would need it to be in polar form, basically. So there are situations where if it's not in polar form, we're kind of out of luck. So we'll look at those later. But for now, we're going to start kind of nice and gently with this idea of polar equations. So we'll look at several polar equations and their graphs. You should try to recognize the patterns, the equations, and know the shapes they make. Okay, so later on we're gonna have shapes. Now we're just talking like lines and circles, but you'll get the gist in just a moment. For this topic, let's focus on circles and lines, specifically diagonal lines. Okay, so example four says identify and graph each of the following. Let me shrink this a little bit to see if it'll all fit. That's slightly better. Okay, so first we have r equals 3. We already talked in the previous video about something almost identical to this. We had r equals 4, and we were able to really super easily convert this to its polar form, or to its rectangular form, rather, and we could see with ease what it was. Now, before we get into this, just as a reminder, once we kind of talk about these, we'll take the steps to actually convert them to rectangular form just to kind of prove that we're right. But we need to remember that r squared equals x squared plus y squared. X equals r cosine theta. Y equals r sine theta. And we also have that tangent of theta equals y over x. So those are some important things that could potentially be useful to us in just a bit. Okay? Now, first, let's just talk about r equals 3. There we go. So in this particular case, we're missing one of our variables. So when we're in polar form, we have r's and we have thetas. Well, in this case, we have an r, we don't have a theta. Okay, so that means theta could be literally anything. It can be absolutely any value for theta. We just have to make sure that r is 3. Okay, so I could choose theta of pi over 4. Well, r would have to be 1, 2, 3. I could choose theta to be pi over 2. Well, then I would still get r equals 1, 2, 3. I could choose theta to be, let's see, that's going to be 11 pi over 6. All right. And as long as we get R is 1, 2, 3, we're good. We could choose, let's do one more color just for funsies. Let's do this like kind of purplish color. We could choose something over here. So let's say we do 5 pi over 4. And again, R is going to be 1, 2, 3. So again, it doesn't matter what theta is. We have free reign. Theta can be anything. We don't have theta given to us. It could literally be anything we want it to be. Okay. And what we end up getting is basically a circle. Okay, so we get a circle centered at the pole with a radius of 3. So this is a circle centered at the pole. And remember, the pole kind of acts like the origin does for us in the rectangular system. So we have a circle centered at the pole with a radius of 3. Okay? And this is just how like if you're missing one of the two variables, then you're kind of limited to the one you got. And so in this case, we're told that r has to be 3, theta can be literally anything. Now, just to prove to ourselves that this is so, let's go ahead and try to convert this to rectangular form. Now, we know that when we have these polar equations, two things that we can try is to square both sides or multiply both sides by r. I want to square both sides. So I would get r squared equals 9. And then remember, just a minute ago, I said, don't forget, r squared is equal to x squared plus y squared. And at this point, we have something that we should be familiar with. This is a circle centered at the origin, okay, with a radius of 3, okay? So just know here we have no specific theta. We could say theta is literally anything. As long as r is 3, we're good. We get a circle centered at the pole with a radius of 3. Okay, now for part B, we have theta equals pi over 3. So let's think about this. In this case, we're missing the r. We have no stipulations on what r can be. We just know that our theta has to be pi over 3. Period. Theta is pi over 3. So let's think about that. So let's say that we open up from the polar axis, we're going to open up pi over 3 radians. So that's going to put us up here. So this is pi over 3. Okay, so we open up pi over 3 radians, and then what? Well, we have to choose an r. It can be anything. We don't have an r. So there's no r. So set it at whatever you want. So we could say, okay, R is going to be 2. R is going to be 1, 2, 3, 4, 5. R is going to be 4. We could also say that R is going to be -2 or -4. Okay, we could say R is anything. So what does this end up giving us? Well, this gives us just kind of like a regular old line. All right, so we know our angle is pi over 3, but otherwise r can be anything, okay? So as long as theta is pi over 3, you could set r to be any positive, negative value. What this gives us is just a regular old diagonal line, okay? Now, converting this one to its rectangular form is a little bit weird, but what we do know is that we have this relationship that tangent of, well, let me write that better. We do know this relationship that we have tangent of theta is equal to y over x. Well, we have a value for theta. So we're like, okay, well, tangent of pi over 3, that's our theta, has to equal y over x. Okay, well, what is tangent of pi over 3? So I'm going to draw a teensy weensy little unit circle over here, or a portion of a unit circle. So we have pi over 3, and at pi over 3, we get that cosine is a half, and that sine is root 3 over 2. Okay? So we have that relationship there. So what does that mean for us? Well, we always want to take x and then, or y, and divide it by x. So we have this right here, y divided by x. So that's going to be root 3 over 2 divided by a half, which is really going to be root 3 over 2 times 2 over 1, or just root 3. Okay, that's easy enough. So we get root 3 equals y over x. We know in the rectangular world that we live in, a lot of times we'll solve equations for y, so let's do it. We would multiply both sides here by x. Well, when we do that, these x's on the right, they just divide out to become 1. So we're left with, let me go back to purple since that's what I started with. We're left with y equals root 3x. So this right here is a regular line with a slope of root 3 over 2. Okay, so again, when you have one of the two variables missing in your polar form, it means something, just like having one of the variables missing in rectangular form means something. So here, when your theta is missing, you can set theta to be anything you want. You could set theta to be literally any value. As long as your r is 3, you're good. And what that's going to give you is a circle centered at the pole with a radius of 3. Now, if r is missing and you have just a theta, that tells you your angle theta is set, you can't change it, but you can let r be anything. So that just gives you a regular old line. And we were able to do a little bit of work here to convert it, but we got the, let me get a different color. We got the rectangular version of both of these equations to kind of back up what we sort of suspected just by playing around with these graphs. Okay, so be mindful if you're missing your r or you're missing your theta, it means something. You either have a circle or you have a diagonal line. Okay, in the next video, we'll do a little investigating with horizontal and vertical lines. They're a little bit different.